Okay, so with that, let's start the last session. We have two talks in this session, starting with Chatterjee, and he would be talking about generalized Kramers-Wannier duality in Hopf Ising models.
Thank you. Can people hear me okay? Right. Thank you, Apu. Thank you, Subhro and Sergej, for organizing this wonderful workshop over 2 weeks. I've learned a lot, and hopefully we've all had a chance to appreciate generalized symmetries. I also want to thank again ICTS for their warm hospitality and making this day really memorable. So this talk is about generalizing Kramers-Wannier. By now, you've probably seen many talks, many posters on generalizing Kramers-Wannier in various different ways. I'll try to show how what we're doing goes slightly orthogonal to whatever has been done so far. So this is collaborative work done with Dachuan and Nat. Dachuan is at Harvard, he's a postdoc, and Nat is a new faculty at Stony Brook. The paper should come out soon, hopefully. I'll go quickly through the motivation because we're on the last day of the program, last session of the last day. So by now, you're probably super motivated about generalized symmetries, and you want to work on that full time. So let me just go through this quickly. Ordinary symmetries from this new perspective can be thought of as topological defects, which are codimension 1 in space-time. So here I'm showing some cartoon where I have 1 plus 1D space-time, and I have defects which are oriented in some way, and they fuse like group multiplication. So these are the ones that you know and love. I put anti-unitary in brackets because I'll ignore them throughout. I think that's an interesting orthogonal direction. Okay, so when you increase the codimension, crank it up from 1 to 2, 3, 4, you get P-form symmetries, which are also known as higher form symmetries. And then if your fusion rules are no longer group-like, so they're not invertible, you end up with something called non-invertible symmetry, which is the subject of this talk. There are various other generalizations, such as subsystem, multipole, modulated, etc. They have all made appearances throughout the last 2 weeks. So for this talk, I'm focusing on non-invertible symmetries, which have been known in the CFT literature for a long time. For instance, back in the 80s, people knew about these Verlinde lines, which are topological. They commute with the stress tensor. So you can move them freely as long as they don't cross any local operator, any defects. But people have also understood how they work on the lattice. For instance, in StatMech models studied by these authors in 2016. And they use these things to help with lattice computation of CFT data, which is something that I thought is like really hard, like computing spins of local operators, which is a continuum concept. The non-invertible symmetries have anomalies, just like ordinary symmetries do. So these anomalies, again, they also provide constraints on allowed phases. Pranay gave an example in his talk, and there were other examples throughout the program. In particular, anion chains have a rich set of symmetries labeled by fusion categories, which were studied back in the early 2000s, and they continue to give many gifts to this day, as you've seen in Apurv and Frank's lectures. There are also, like, non-invertible symmetries are not only in these somehow quote-unquote fine-tuned models, they also appear in generic ordered phases as emergent symmetries. And there are new gap phases that you can construct with these non-invertible symmetries. So basically, whatever you can do with traditional symmetries, you can do with these non-invertible symmetries as well, with some minor caveats. So here, let me first recap Kramers-Wannier, which I'll go through quickly since Pranay gave a beautiful talk yesterday. So this has to do with the 1 plus 1D quantum Ising model, and the Hamiltonian, which by now you've seen like infinite times, has a single a single dimensionless parameter, which is h over j. And as you tune it, you go through a phase transition between a ferromagnet state and a paramagnet state. There's an invertible symmetry, which is product of x on every site, product of poly x on every site, and that that is spontaneously broken for small h. And the infrared CFT is the well-known Ising CFT. And the Kramers-Wannier duality acts by sending a single x to a pair of z's on neighboring sites and a pair of z's to the next, to the poly x on the next site. Okay. And there's a lot of work in this direction, not only on this model, but related models which show similar symmetries. So in the CFT literature, it started from the 90s, and on the lattice, of course, Kramers and Wannier, but they were studying StatMech systems. More recently, in Asen, Fenley, Mong, in 2016, they considered like quantum lattice models by essentially taking an anisotropic limit of a StatMech problem. Okay, so that's the Kramers-Wannier symmetry. I'm going through this fairly quickly because we've seen this a few times now, but please interrupt me with questions whenever you have them. So what we can observe is at the critical point, this transformation is a symmetry of the Hamiltonian, meaning it commutes, if you write down an operator that implements that, commutes with the Hamiltonian, right? So as you evolve in time, that operator is a conserved operator. What is that operator? I'm going to denote it with D sub KW. I didn't write down the expression because we already saw that, but there's a matrix product operator expression, there's a sequential circuit representation, there's various representations for it. But the invariant thing is that these are the fusion rules, or rather, this is the Hermitian conjugate, and here are the fusion rules. Importantly, this operator must be non-invertible. So if you actually explicitly write down an operator and compute its determinant, you'll see that it's 0. And a quick way to see that is like by looking at this relation. Yeah, so D times D dagger doesn't have a translation, so it's just a regular operator. Take the determinant on both sides, and you see that this operator must have determinant 0, so it must have a non-trivial kernel. In the IR, so we know that this Hamiltonian flows to the Ising CFT. What does this operator flow to? It must become some operator in the IR. It flows to a topological defect line called curly D in Ising CFT. It's a non-invertible line, meaning if you compute the fusion rules in the CFT of this line with itself under parallel fusion, you get this fusion category, whatever that is. Essentially, it contains an invertible line and a non-invertible line, which fuse like this. So it's very reminiscent of this symmetry algebra. The key difference is that there's a lattice translation here, and that's where that's where some of the interesting features of the lattice Kramers-Wannier lies. Okay, the way these two are consistent is that the translation operator acts trivially in the IR theory. So it flows to the identity operator. So these two are completely consistent. Okay. So how do you construct this operator? One way is by gauging. And in Apurv's lecture, we saw how to gauge Z2 symmetry on the lattice. So you start with a chain. I'm in 1 plus 1D, so I'll not be drawing plaquettes. So you start in a chain with these black sites. I label the links with half integer degrees of freedom. To begin with, you only have degrees of freedom on the integer sites. You consider operators that are in your Hamiltonian, so you have these local ZZ terms, local X terms. And then you need to introduce some new degrees of freedom, gauge field degrees of freedom on the links. And when you do that, you want to define a Gauss operator, which essentially localizes the action of the symmetry. So symmetry operator is product of X. You localize that to one site, and then you demand that you'll modify this to introduce a Z2 action on the links as well. And then you need to modify your Hamiltonian such that all of the Gauss operators commute with all of the Hamiltonian terms. So that means, that is a complicated way of saying minimal coupling. So you modified your ZJ plus 1 type term to have a poly Z acting on the intermediate link. And then you do some unitary transformation, which is a bunch of control X's, which makes the Gauss operator local. So this is the Gauss operator in red. It becomes just a single site X, but it modifies the Hamiltonian terms. And then you implement the Gauss law. So what is the Gauss law? The Gauss law is this red guy. It's nothing but setting x equals 1 on all the sites. Right? So that you perform that projection and you get this. That's your gauging map. It's a bunch of steps, like very algorithmic. Given any Hamiltonian, you can do this. I'm just showing the simplest Hamiltonian for illustration. It's an algorithmic procedure. But then to go back to the original Hilbert space, I need to shift these operators back to the original sites, and that's where this translation comes in. If I want to think of this whole thing as an operator that's acting on the Hilbert space and bringing you back to the same Hilbert space, you need that translation. Okay, so this is the gauging map. You went from ZZ and X to Z and XX. You see that we're still not really back to the same Hamiltonian because you have two X's and one Z. So how do I fix that? Well, I apply some unitary transformation, the Hadamard gate on every site, which turns Z to X and X to Z. And that gives you this. So essentially there's two steps. There's a gauging and then there's an isomorphism. This is crucial to what I'll talk about because in the more general context, this isomorphism is not something like we're super familiar with. It's not already, it's not obvious. It's a non-obvious isomorphism. So generally, like you'll go from a Z2 symmetric system to what is called a Reb Z2 symmetric system. But it's a math fact that Reb Z2 as a category is isomorphic to vector Z2. And that's why you were able to kind of get this self-duality to begin with. Okay. So as a circuit, I can write this whole operation like this. So you can check that all the steps that I did, you can kind of track that through this circuit. So minimal coupling, unitary transformation. So this first step is kind of like minimal coupling. I'm introducing the ancillas or the gauge field in some trivial state. And I'm coupling them using this bunch of C naughts, CX's, control X's. And then I do some projection on the sites. Okay. And as Pranay taught us, there's a super simple way of representing this using what is called ZX calculus. I leave this as an exercise to people who watched Pranay's talk, how to write the previous circuit as this. But the advantage of this representation is that you can really quickly simplify this to this. So this horrible looking mess is not really that horrible. You can simplify it to this and even pass that through. So it's a very symmetric, like translation symmetric representation of this whole circuit. Okay. Any questions up to this point? Right, so yeah, so these are the same tensors that appeared in Pranay's talk. Let me write it. So this green tensor usually appears in text as a hollow circle. This is the GHZ tensor, or in other words, if you had 0, this 0, 0. You had maybe another way of writing this is if you have x, this is x. For 0, it will be 0, 0, it will copy 0. It's 1, it will copy that. Same for the upside down, you can copy in the opposite direction. And then, like, if you pointed everything up, that would be the GHZ state. That's why it's called the GHZ tensor. And then the box, the yellow box is the Hadamard, which squares to 1 in this case. Okay. So that's the ZX calculus representation for Kramers-Wannier. And the goal of this talk is to find some diagrammatic calculus like this for more general non-invertibles beyond the ordinary Kramers-Wannier. So before doing that, let me at least classify some of the known constructions of Kramers-Wannier type symmetries. So I asked 3 questions of every construction. Does it mix with translation? So if you look at the algebra under like products, under fusion, does it mix with translation? Does it act on a tensor product Hilbert space? And does the identity element act trivially? So is the identity element represented in your symmetry algebra as the identity operator? I asked these 3 questions. And so the type that I just talked about, which is self-dualities from gauging abelian groups, they sometimes mix with translations, sometimes don't. There are known examples where it doesn't mix. For instance, this rep-D8 symmetry of cluster state. But they all act on tensor product Hilbert space. Identity acts trivially. When you get a rep-G symmetry from gauging a non-abelian group, that doesn't mix with translation. It acts on a tensor product Hilbert space. Identity acts trivially. So this is kind of like the goal for us here. I want to look at, or okay, I shouldn't say the goal, but this is like the nicest type of symmetries that you can have. It's a completely internal non-invertible symmetry. There's no mixing with lattice symmetry. It acts on a tensor product Hilbert space, things like this. So there are now the any on-chain constructions, which already gives up the tensor product Hilbert space, but it doesn't mix with translation. So you can, that's like kind of a trade-off between the two. And there are also MPO representations of what are called weak Hopf algebras. I'll be talking about Hopf algebras, but weak Hopf algebras are slight generalizations. But one funny thing there is the identity element acts in a non-trivial way. So if you wanted the identity to act trivially, that's like projecting to the identity symmetric sector. So if you want to get a check mark on here, you lose this. You lose the tensor product. There's some interesting interplay going on between all of these 3 things. It's a non-trivial operator, so maybe I'll comment on that when I'm going along. Like, yeah. So like meaning that if you have an operator algebra, and there is a non-trivial operator that's acting like an identity, meaning multiplied with anything else, it gives back that. So it's an identity in that sense. But on my Hilbert space, it doesn't act like identity. Okay, I should say that this is not like, here I'm just being very general. So like in any on-chains, you can obviously like reconstruct tensor product Hilbert spaces. But I think the question is, for given any fusion category, can I get a tensor product Hilbert space realization? That's unclear. All right, so in this talk, I'll show you examples of both this and this type. But we'll go beyond the first row by gauging non-invertible symmetries. So it won't be an invertible gauging, abelian group gauging. So there are 3 questions that are kind of in this area. And we'll mainly be focusing on this first 2. Which non-invertible symmetries can I realize on a tensor product Hilbert space? And how do non-invertible symmetries generally interplay with translation? There's an interesting open question in the context of CFTs where, given any fusion category, can you show me a CFT that realizes that as topological defect lines? In particular, for C equals Hagerup, that's for the experts in the audience, there's a fusion category which is finite, very nice. But there's no known construction of a CFT, at least analytically, that realizes this symmetry faithfully. But we won't be talking about that problem. I just wanted to throw that out. Okay, so that's my extended motivation, which took half the time. And here are the main takeaways. So we'll develop this diagrammatic calculus for Hopf algebras with generalized ordinary groups. There's going to be a completely internal type of representation of rep H symmetries. H is a Hopf algebra here. Doesn't mix with translation. And whenever H is self-dual, I'll define that shortly. We'll construct a Hopf version of Kramers-Wannier. We'll look at a specific example if time permits. So let me start with an intro/refresher to Hopf algebras and Hopf ZX calculus. This topic was developed by these people, and there's not a lot of literature on this actually. So Hopf algebras have been known for a long time, but developing a complete graphical calculus is a much more recent interest. So a Hopf algebra consists of these 6 pieces of data. There's a vector space. I'll take it over C, over complex numbers. There's a multiplication. So all diagrams will be read going from bottom to top. You're multiplying this leg with this leg. So it's some linear map from H tensor H to H. Identity is some element here, which fuses nicely. I'll talk about that in a second. Co-product is kind of the dual of multiplication. From one thing in H, you can get two things tensor. And then there's a co-unit for this and something called an antipode. These things satisfy a bunch of relations. So for instance, multiplication and the identity satisfy this. So if you multiply the identity, you get the identity, If you multiply the identity, you get nothing basically. So this is like doing nothing to your, to this leg. Similarly here, if you do a co-unit on the co-product, it's like doing nothing. So you can think of this as this red circle annihilates with the red circle, green circle annihilates with the green circle. And the co-unit and the product have some nice relation. The unit and the co-product have a nice relation. Co-unit and unit are normalized in some sense. And then there's these bi-algebra and Hopf rules. So Pranay mentioned this Hopf rule, but in the case of Z2, this antipode is trivial. So you can ignore this S. But in more general cases, you need an antipode. Even for groups beyond Z2, like Zn, you have an inverse here. There's a further simplification because we are dealing with semi-simple Hopf algebras. Why are we dealing with semi-simple Hopf algebras? It's because we want the representation category to be semi-simple. And this is the kind of symmetries people talk about in QFT. These are where the lines can always be decomposed into some simples. So this is not a very drastic assumption. So we'll be working with semi-simple H, and for this, S is always self-inverse. So S squares to identity. So you can always kill two S's in pairs. So that's kind of the structure. This is the structure of a Hopf algebra. There's a bunch of linear maps which interact in some ways. Yeah, I'll talk about that in maybe order 10 slides. So let's give an example. So this is Pranay's example, right? You had CZ2 as your Hopf algebra. You can think of this as like, I take my basis as 0 and 1, which are the elements of Z2, and I put some complex coefficients. Those are all the elements in this vector space. And I can define these tensors all on that basis, and then everything else just you can extend linearly, right? So the product is just the group product. So 0 tensor 0 would give you 0, 0 tensor 1 would give you 1, and so on. So this multiplication is really addition in this presentation. Similarly, the green tensor gives you a copy rule, like I was saying on the blackboard. So you can easily generalize this to any group. It doesn't have to be invertible. It doesn't have to be abelian. Group has to be invertible. And the generalization is that the product is still the group product. The co-product is still copying. But these things get slightly modified, and you need to introduce an inverse. So the antipode plays the role of an inverse. So we'll soon leave this arena, but let me just comment something. So whenever you have an element in a Hopf algebra that has this co-product, it's called group-like. So in a general Hopf algebra, you can have some elements that behave in a group-like manner. So when you do a co-product, you just get a tensor. But okay, so more generally, what you get is the co-product of G is denoted in a notation very similar to Einstein notation. So I get two things, and I get a linear combination. But in general, this may be the number of elements over which I'm summing is not fixed. So this is known as Sweedler notation, which is reminiscent of index contraction. So more generally, you'll have a sum of different things here, not just a G tensor G. Okay, so for any Hopf algebra, one can construct a dual. Basically, take your vector space, consider its dual, meaning functions from that vector space to complex numbers. That also has a Hopf algebra structure, it turns out, and I can define all of the data. Here I've kind of defined that. So the dual product denoted like this is basically this. You flip the legs. The dual unit is related to the co-unit, and so on. So you see the colors are kind of just changing, right? All the co-product is defined in terms of the product. So maybe it's I don't know if it's helpful to write down some algebraic expressions. So for instance, let me write the dual co-unit here. The dual co-unit is some function acting on something. So let's call that X. This is defined as now having a brain freeze moment here. Okay. Should be a delta function in some sense. Right. Okay. Okay. I'll have to double check this. Anyway, so you can construct the dual Hopf structure starting from the original ones by replacing how S dual acts on functions to how S acts on elements of the Hopf algebra. Actually, was there any question about this? I know it was a little confusing. So there are also these special states called the Haar integral state, which is denoted with a green circle here. When you product anything else, you just get back the Haar times co-unit. Doesn't matter which way you multiply. There's some normalization which will be helpful for us, but it's a fact that all of these Hopf algebras have a unique Haar integral. So there's some unique state that satisfies this property, and we'll denote these things with L and phi. And with this thing, with this Haar integral, you can define caps and cups with both colors. These are the things that will let us kind of bend legs in this modified ZX calculus. In ordinary ZX calculus, these things are trivial, so you don't need to keep track of them. But in this more general case, whenever you bend a leg, you have to introduce this Frobenius form. All right, it's a bunch of structure. You don't need to really remember all these details. I'm just saying this to kind of motivate the diagrammatic calculus. And there's also some nice properties, meaning if you have two of these in the same color, you can straighten that. And then there's some normalization. When you have opposite colors, you get the antipode. That tells you how to combine like red and green circles. So let's think of a specific example. In this case, I picked a general group. The Haar integral is a sum over all group elements. It's a fully symmetrized state. You can think of this as the plus state in the Z2 case. This is a function acting on those things. So you can think of this as a bra state. So this is a delta function, meaning if you get anything other than the identity coming up here, you'll kill that. So you can think of this as a bra identity. And then, okay, you can work out all of these other things. In this case, actually, it's enough to focus on the top row. This is just different by some inverse. So this state is like G and G inverse. So you can think of this as a G and C state on two links. So 0, 0 plus 1, 1 in the group case. And this is the bra corresponding to that. Together with this Frobenius form, one can also define the tensors with like opposite color. So remember this 2 legs going to 1 was red, and 1 leg going to 2 was green. But with this additional data, you can turn around these legs and make these opposite looking tensors. Yeah. Right. So every diagram is completely planar. So whenever there's yeah, the crossing doesn't matter. So I mod out by crossing. Yeah, it's a good question. Okay. Good. So every Hopf algebra, it turns out, has this structure, and so you can always kind of define a Hopf algebra as a Hopf-Frobenius algebra, at least in the setting that I'm talking about, semi-simple, etc. And so you have these Frobenius relations, which are sometimes called I equals H relations, because these look like H and these look like I's. But then you have one for each color. There's two Frobenius algebras sitting inside this Hopf algebra. All right, so all of this was just some math. Let's look at some lattice models. So to actually construct a lattice model, I need to define a Hilbert space on which my operators will act. Right, so I need to define what is a Hopf qubit. So I want to think of the Hopf algebra itself as a qubit. It already has a vector space. I need to define an inner product to define a Hilbert space structure. So for that, we need to define a star. So what is a star? Sanjay already talked about this in his talk. So essentially, it's what tells you how to turn an operator into its dagger. The more general setting is this von Neumann algebra, C-star algebras, but here, because we're again working with finite dimensional Hilbert spaces, it's much simpler. You'll see. So using this star, which is an antilinear map, I can define an inner product. I just turn A to its star, multiply with B, and then take the dual of the integral, so dual of the Haar. So this whole thing gives you a number. You start with two things in the Hopf algebra, and you kind of contract with this function that ends up giving you a scalar. The normalization is such that the unit has a unit norm under this, but it's not super important. Okay, so with this inner product, I can now define a Hilbert space structure on this Hopf algebra. Here I'm just saying how you define adjoints in the normal way, like you take O dagger acting on the left, and that's defined by this relation. You act with O on the right. Okay, the dual Hopf algebra also has a star structure, but it's not super important here. With these things, now we can start talking about Hermitian operators acting on a Hopf algebra. Yeah. It's complex. Yeah. That's a good question. Yeah, one way to see this is that it's antilinear in this first entry. You put a complex number here, because this star is an antilinear map, you get some C bar here. Yeah. So it's like a sesquilinear form, I think. Great. So now I'm ready to actually do spin chains. I can define operators like this. For instance, I have a poly X operator which just multiplies some element from the left. There's a right multiplication as well with an inverse. I can also define Z operators. So this thing, it takes a co-product, so it branches out a leg, and you act on that with some function. So alpha is some function. You can think of it as an element in H dual. It acts on this second leg, or you can act on the first leg. Importantly, you can't swap the legs generally. Because this is not like a G going to G tensor G symmetric coproduct, you can't generally like swap the legs. So this left to right ordering is important. Or which way you enter a tensor is important. The multiplication of the X operators follows the multiplication of the Hopf algebra. Multiplication of the, oh, sorry, this should have been a Z here, it's a typo. Multiplication of two Z operators follows the coproduct of the Hopf algebra. So X is kind of like, X is a, X behaves like multiplication, Z behaves like co-multiplication. You can also define some two-side operators. These are generalizations of C naught or CX, but we call them ZX. The pun is not intended. It's called ZX because you have a Z tensor here and an X tensor here. That's the reason I call it ZX. These these operators, just like the ordinary C0 and CZ, they're all unitary. So remember I defined the inner product. I can define what dagger is. I can check if dagger times itself is identity. And you check that indeed, like this and this are inverses, this and this are inverses. So you see where I'm going with this. I'll use these things in my C0 layer of my gauging later on. Okay, any question? Yeah. This should be a Z. Yeah, these are all typos. Sorry. Yeah, this both should have been Z. Yeah, thank you. Good point. Questions? I have 4 minutes. All right. So now I want to define symmetry operators out of these local tensors. So when I define the symmetry operators, they're going to be labeled by elements in rep H, objects of rep H. Rep H is the fusion category of H modules. It's generalizing representations of groups. And for any, this is a math fact, any non-anomalous fusion category is isomorphic to some rep H. And this is the crucial result that like makes this whole story powerful. Essentially what we're doing here is using these Hopf qubits, I'm giving you a lattice realization for any non-anomalous fusion category symmetry in 1 plus 1. In a diagrammatic way, but it can also be turned into an MPO. And here's the operator that implements rep H. You pick some representation gamma. It has some A-rep indices, which I denote in blue. And you attach that to the green tensor on every leg. And then take a trace. And this uses like representations. Yeah. Yeah, trivial gap phase. I think I mean isomorphic. Yeah. So for any such fusion category, using the fiber functor, you can reconstruct H. And you can go the other way by just taking the representation. Oh yeah, you can define it like this with an S. You can define it without an S. There's like 4 different versions of this. It's like left multiplication versus right multiplication for group symmetry. In the group case, rep G case, this doesn't matter because you can swap the legs, but here it will matter. Okay. Other questions about this? Okay, so you can do this game also with the dual Hopf algebra. Before going there, actually, let me comment on one difference between this and rep G. In the rep G case, these operators are diagonal in your basis states, but here it won't be diagonal because of this peculiar structure of that tensor. So this is like what it looks like. You pick up the second leg from every site, and then you have a superposition over various basis states. And it's clear that if you like box these two together, it's an MPO. Right? This gamma and this tensor together, think of that as a box. That is an MPO with dimension equal to the irrep dimension. It's an MPO with bond dimension D gamma. It's also clear that the fusion of these things don't mix with translation, as I just showed on the last slide. You multiply 2 of these, you get a sum over other D gammas. Okay, so this is actually this was actually studied in these papers. This more recently. The difference here is that we are giving a diagrammatic expression which you can write down for any Hopf algebra. So I just give you the Hopf algebra data, and looking at this, you can construct for me what the symmetry operator is. So there's no like secret sauce here. It's all there. Okay. Yeah, like I was saying, you can construct these this symmetry operator also for the dual Hopf algebra. So take a representation of the dual Hopf algebra, play the same game. The difference now is that it acts from the left and from the bottom. Now it acts by multiplying rather than co-multiplying on these qubits. It also has a bond dimension D gamma, and the algebra follows the fusion rules of rep H dual. I'm going a little quick here, but X sub R, you can think of R as a character in H dual, and X sub R is its character. Sorry, R is an irreducible representation of H dual, and XR is its character. But because characters are functions from the Hopf algebra they're acting on to the dual, essentially this is an element in H dual, which is just H. So this is an element in H, that's why this makes sense. I'm co-multiplying something that's in H. It may not be clear from this expression that this is translation symmetric, but essentially because characters are co-commutative, you can show that this is indeed translation symmetric. You can also write a translation symmetric MPO. I can go into that later. Okay, I should wrap up. Here are some simple models that have this symmetry. You have some paramagnet term and some ferromagnet term. Diagrammatically, they look like that. And indeed, you can check that you get a symmetric ground state when H is large, when all the H's are large. And when all the J's are large, you get symmetric breaking states with degeneracy. So where do these things come up? Like I've been constructing all these kind of contrived looking examples so far, but do these appear in simpler models? Indeed they do. So for instance, rep H8 is a Hopf algebra. It appears in 2 copies of Ising. So essentially the construction of this non-invertible guy there is coming from 2 Kramers-Wannier. So you have 2 chains, 2 critical Ising chains. You take the Kramers-Wannier operator for each, multiply them. That operator generates for you the rep H8 symmetry, which as a fusion category, it looks like this. This is the fusion rules, but on the lattice, it mixes with translation. So the contrast between this and what we just discussed is that if you had H8 Hilbert spaces, I can construct for you a rep H8 symmetry, which doesn't mix with translation. Okay, let me move on, unless there are questions about this. So now, because we've done all this, yeah, sorry. I don't know. Yeah, should be possible. Rep H8 is a subcategory of Ising squared. Here we were only looking at some of the symmetries, not all. So now that we've done this heavy lifting of generalizing CZ2, which is qubits, to Hopf algebras, we can immediately read off the answers for gauging maps, Hopf Kramers-Wannier, etc. So this is the version I claim, which is a generalization of the Z2 case. The main difference is that I've introduced the antipodes. Antipode was trivial there because the inverse was trivial. It's exactly the same expression as before, if you remember from about 15 slides ago. And yeah, this has been studied in many interesting recent papers. This is doing a much more general job of gauging any algebra object, but here we are gauging the full symmetry. Okay, so that's the gauging map. I still haven't given you the Kramers-Wannier because when you gauge this symmetry, you get the dual symmetry. So you go from A's to the B's. And okay, you can convince yourself of that in many different ways. But I want to construct self-duality. So then I need to restrict to self-dual Hopf algebras. And these are Hopf algebras which have an isomorphism between the dual and itself. That's why it's called self-dual. And for these things, you can define something called a Hadamard. So Pranay, to answer your question, there is a map from H to H, linear map from H to H, which is unitary. And it satisfies these color changing rules. You change the color of the red to the green, green to the red to green. There's some twists going on. So all these relations are simultaneously satisfied. So now if I act with this F dagger, that will turn the rep H symmetry B gamma back to the rep H dual symmetry. So you started with A symmetries, you gauged, you went to B symmetries, which is like rep Z2 or product of Z in the Ising example. But then you did this unitary transformation, you made a change of basis, and you went back to A. So with this, you can write down the ZX calculus representation of the Hopf Kramers-Wannier, and a quick calculation will show you that that's equal to this. So this is like this translation symmetric MPO representation. So there's daggers here, which just means it's the dagger of the Hadamard. And undaggered ones are this, the Hadamard. And you can check how it acts on local operators. I'll leave this as an exercise. And then let me quickly flash the results for H8. So H8 is an 8-dimensional Hopf algebra, which is self-dual, and is the smallest like non-group-like example. And unlike group algebras, for these general Hopf algebras, there's no special canonical basis. So here's one choice of basis where all the data is written out in gory detail. And the fusion category is a simple type. Is there a question? Okay, you can write down the irrep matrices, but okay, this is not super important. What is important is that there are 3 non-trivial 1D irreps. So these are all 1D irreps. And there's 1 non-trivial 2D irrep. Great. You can write down an Ising model with this. So you can write down X terms and ZZ terms. I've put a K as a relative weight between 1D and 2D irrep. All the 1D irreps are added in a symmetric manner. And then you tune J. As you tune J, let's say K equals 0. You go through a first order transition, it turns out. But when you turn on K, you go through a multi-critical point, which then splits into a bunch of different transitions. These break various subsymmetries in various, like, they are partial SSB phases with different ground state degeneracies, which I'm not going to get into here. This multi-critical point is it's still unclear what this is. This is a CFT. What is the central charge? From numerics, we seem to find some large central charge, but it's unclear. We have some bounds, but we don't know exactly what universality class that is. So that would be an interesting, on this entire line, you have this self-duality symmetry as well as the rep H8. So it's a self-dual gapless state. Okay, there's many interesting features here, but I'll not go into that. So I'll just quickly say a few words about outlook. So it's not clear whether this Hopf ZX calculus is complete in the same sense that ZX is. It has been proven in the Z2 case. And the other kind of broader question I would say is, how do you axiomatize non-invertible symmetries on the lattice? With that open question, I'll thank you.
A quick question or two, Abud?
You're asking, can I do it by measurements and feedback? Yeah, that's a really good question. I think a simpler question would be, can I do so that's a question about the gauging map. Maybe a simpler question would be for non-abelian groups, can I do that? Right, so like, right. I see what you're saying. I haven't thought about it, but yeah, it's an interesting question. If the self-duality like gives you some extra mileage.
Maybe one more question, if there is one. Okay, I don't see a hand. So let's thank Orko once more.
Thank you.